All right. I looked at the agenda, and it looks like I'm either in your lunch or I'm between you and having lunch. So let's try to stick to the schedule here. Welcome to this talk. Talk is called "Let's Refresh Our Memory Management in .NET." And if you are here for the really in-depth, hardcore stuff, then I'm sorry, I will have to disappoint you. The idea of this talk is to refresh your memory about memory management in .NET and to look at a couple of things that may matter in your applications. But the good news is that the agenda has a couple of really deep dive talks that continue to build on the stuff that I will be talking about. I'm Maarten Balliauw. I work for JetBrains and I flew in from Belgium. And yeah, let's dive in. So if we look at the .NET runtime and you have your application that you're building and you want to run your application, you'll see that the .NET runtime does a lot of things for us. It basically runs our application. It does just-in-time compilation, converting the intermediate language code of our application to something that can run on the CPU in on your computer. It handles type safety so that you can actually work with different types and ensure that something is a string, something is a person class or an address class, etc. It does exception handling and so on. And we're not going to cover those things. We will just cover the thing that it does really well, and that is memory management and garbage collection in the .NET runtime. So if you look at memory management and the garbage collector in .NET, you'll see that its goal is basically to give you virtually unlimited memory in your application. It does that by, when you start your application, it does that by reserving a big chunk of memory for your .NET application. So that whenever you want to allocate something in your application, you don't have to go to the operating system and ask for more memory to allocate the variables that you want to have there. Instead, it allocates a big chunk of memory, and whenever you allocate something in .NET, that will be stored in this big chunk of memory called the managed heap. Now, virtually unlimited means that whenever something is no longer being used, the garbage collector will run and remove the objects that were stored in this big heap, so to free that up and make it available for future allocations again. So it frees that up and makes it available and gives you the impression that memory is unlimited and you can store whatever you want in that managed heap. Now, if you look at memory allocation, those things go in the managed heap. And allocating memory in that managed heap is really, really fast. The reason for that is that .NET doesn't have to go to the operating system again. Reason is that it can just allocate a pointer in this big heap and then allocate your object and make it available in there. Of course, if you attach a profiler to any .NET process, you will see there's this big chunk of managed memory that it allocates, but there's also some unmanaged memory being allocated where it stores graphics, buffers, and whatever is needed to make your application run, but we'll not dive into that one in this talk. Now, at any point in time, the garbage collector may run, and it may release the objects that are no longer in use by your application. So what will happen is that the garbage collector pauses your application, looks at all the objects that are in memory, analyzes the graph and looks at which objects are still in use. And if the object is no longer in use, if it's unreachable from any other objects, it will be marked for removal and removed from memory eventually. And what will also happen is that the garbage collector will compact that memory. So if you think of defragmentation on your hard drive, for example, what the garbage collector will do is defragment your memory space as well, so that whenever you want to allocate something, there's always a big chunk of memory available where you can just have one stream of bytes available to store the things that you want to store in there. Now, the problem with garbage collection is that it takes time to scan all the objects that are in memory. So the garbage collector will have to pause your application and scan all the objects that are in memory, see if they are still in use, and that may take some time. The bigger the chunk of managed memory that is available or made available to your application, the longer this time will take, of course, so that's not ideal. So Microsoft came up in .NET with the idea of splitting this big managed heap into generations. Whenever you first allocate something in memory, that allocation will be done in generation 0, just a part of this managed heap. Whenever the variable that you allocated goes out of scope, it is no longer reachable, and when the garbage collector runs, it may remove it from memory if needed. So if you have short-lived objects, imagine a function call or a function where you have an allocation and at the end you return. Well, that's a short-lived object, and the object may go out of memory after that. So whenever you allocate something in .NET, it goes into generation 0 first. When the garbage collector runs and decides that the object is still in use, the object will be moved to generation 1. If no longer in use, it will go out of memory and the memory will be made available again. Same thing happens in generation 1. When the garbage collector runs on generation 1, it will check, is the object still in use? If it is, it will move to generation 2. If not, it will go out of memory again. Same thing happens when the garbage collector runs on generation 2. If it's still in use, it will just stay in generation 2. If no longer in use, the memory will be reclaimed and made available again. There's actually a fourth generation, and that fourth generation is called the large object heap. This is where big objects go. If you have a huge array that contains lots of strings or person objects or whatever object that you have in your application, those will typically go in the large object heap. Those are only collected, so the garbage collector runs on the large object heap as well, but they're only collected if all generations are being collected at some point. So garbage collection runs less frequently on the large object heap. By default, the large object heap is also not being compacted. So the defragmentation process that exists there is not always being run by default on the large object heap. And that means if you have to allocate a big object again in this large object heap, eventually you may run into an out-of-memory exception. And that out-of-memory exception may be a lie in some case, because there is still memory available, but there's just not a big enough region of memory available to store the objects. So if you have big objects and so on, you may want to tweak the garbage collector settings to also do compaction on that one to avoid this type of out-of-memory exceptions in that case. Now, the garbage collector runs really often for generation 0 because whenever you allocate something, there's a big chance that after a couple of lines of code or in between two garbage collections, the object will be unreachable and can be removed from memory. On the higher generations, it runs less frequently, and the reason for that is if it's on a higher generation, the chances that the object is still being referenced somewhere are much bigger, and hence it will take longer to scan the entire object root or object graph and check if the object is actually still being used or not. Now, that's all fine. The only issue is that on the higher generations, because the object tree will be larger, garbage collection will take a little bit longer. And also that is not a real problem, except when it becomes a problem. I've seen generation 2 garbage collections with big object trees and so on, where garbage collection would take a couple of seconds and even up to a couple of minutes I've seen in some applications. And that could be no problem, but it could be a problem as well, because when the garbage collector runs, it pauses your application, or in future garbage collectors where background garbage collection happens, it pauses just a couple of threads, but still part of your application may be paused when garbage collection is running and not be serving whoever is using the application. So imagine you have a web application and you have a garbage collection of a couple of seconds. That means that during those couple of seconds, no garbage or no requests will be processed and your application will seem to hang. So that's not ideal, and that's why we want to help out the garbage collector a little bit about being smarter and having to run less frequently or at least less long to scan all the objects that are in the object tree there. Now, when does it run? I have still to encounter a document that really documents all the different points where the garbage collector runs, but people have been experimenting and looking into the garbage collector, and typically it runs on out-of-memory conditions. When no memory is available, let's first try to reclaim some memory, see if some memory is available. When you do significant allocations, that's also typically when the garbage collector will run, and that's a really important one, because if you allocate lots and lots and lots of variables in your application, chances are really high that the garbage collector will run immediately after that and may pause your application at that point. Of course, there's some other places where the garbage collector may run as well. You can force it by calling gc.collect. You can attach a profiler and let the profiler do a garbage collection and so on. But still, Probably the most important one here is after you do a significant allocation or when there's no memory available, and it should check if memory can be made available. Now, one important one also is that the garbage collector is not guaranteed to run. So if you have a big application and none of these conditions really happen in your application, it could well be that the garbage collector doesn't even run. Now, in case you want to see or discover when the garbage collector runs, there is actually the source code of the garbage collector is available online. So if you go to GitHub, you will see that it's available, and it's I think it's about 60,000 lines of codes or 40,000 lines of codes of C++ code. So if you find when it really runs and what the real conditions are for the garbage collector to run, and I'll keep scrolling, please tell me, I would like to know this. Also, if you want to write your own garbage collector in .NET Core, you can actually replace the garbage collector. So this could be a good starting point to write your own one, if you want. Right. So having seen all those things, we probably want to optimize our application a little bit, and we want to make sure that garbage collection either doesn't have to happen so many times, or that garbage collection takes less time to basically shorten those pauses that the garbage collector will make. One way of doing that could be optimizing our allocations, using structs when it makes sense, using the new span of t's, stack allocs, object pooling, things like that. That's one way of doing it. The problem there is that a lot of those cases where you think it could make sense may actually shoot you in the foot later on because you're allocating on the stack and no longer on this automatically managed heap in .NET. But still, if you know what you're doing, that could be one way of having less stress on the garbage collector. Another one could be to make use of iDisposable and the using statements to optimize cleaning up things and basically telling the .NET runtime that you have already manually cleaned up some of the things that your object has referenced. To make it easier for the garbage collector to run everything there. Another thing you could do is make use of weak references in your code, where you basically have an object that points to another object, but when the garbage collector runs, it may clean up that reference by itself. You're basically telling the garbage collector that the object that you are referencing, it can clean it up at any time, and I will take care of reinstating the object whenever it is needed. Another option is implementing finalizers on your object and basically do the cleanup yourself so that the garbage collector no longer has to do this. But beware, because that's the last point where you can actually run some cleanup steps. So if you have a memory leak in your finalizer, the memory will always leak and never be reclaimed again, and you're actually making things worse. So beware of those. Now let's look at one example where we can help the garbage collector. And this is going to be interesting because I'm looking down there. I have an application here, and by the way, if you look at this GitHub repo, you can find all the demos that I'll be doing during this talk. You can find them on there with comments on what to do and what to profile and so on. So feel free to do that when you're back home. So I have a class here in my project, and that class is a sample disposable. Now, for a minute, forget the fact that it's disposable. So imagine it's built like this. And my class has a file stream that it references, and it has an integer pointer that it references. Now, what would happen if I would allocate, let's go to that method. What would happen if I allocate 10,000 objects and then expect the garbage collector to clean them up? So my code here is create a new list of sample disposables that are not disposable, add 10,000 of those into memory, then at some point clear those objects from, or clear that list and expect them to go away and run garbage collection. I would expect that in this case, my sample disposables are cleaned up. Well, turns out if we profile this application, we get a really nice snapshot, really nice profile there, where we can look at the objects that are in memory. So if we look at the first snapshots that I collected, which was right before I run the garbage collection in my code, you will see that in the objects, I actually have of type sample disposable, there's 10,000 of those. So my code works as expected. I actually allocated 10,000 of those objects, and I expect them to be disposed at a later point in time. Then in my code, I ran the gc.collect and expected those objects to be gone from memory. And in fact, if we look at the objects in this snapshot and we search again for our sample disposable, we see that only the list is there and the internal array of that list, and our sample disposables seem gone. Well, actually, they are not gone. If we look at the automatic inspections in .memory here, we will see that instead of having them in the garbage or in having them collected, my sample disposables have moved to the finalizer queue. So the garbage collector ran, moved all these objects into a different set, into a different queue, basically saying, okay, look, I cannot yet clean them up, but I'll queue them when I run next and I will clean them up then. So the objects are actually still in memory. The garbage collector has to run cleanup twice in this case. It has to run them first to collect everything and move them to the finalizer queue, but only on the next step, the finalizer queue will be emptied and basically the objects will be removed from memory. So that's not ideal. So let's look at our source code again and see if we can write a better way. So right now, we implement iDisposable, and what our dispose will do is it will dispose of the file stream that I'm referencing, and it will also free the integer pointer that I had allocated earlier. Basically helping the garbage collector to see that I no longer have any outgoing references to other objects in my own objects. Well, if I use this one and I run my code again, where I again allocate 10,000 of those sample disposables, then I actually call the .dispose method to clean up the references that I have in there, and only then run the garbage collection. We will see in the profiler that the objects will be removed from memory. So let's look at that as well. So in my snapshots that I have here, I have a snapshot that I took right after allocating those 10,000 objects, and you will see that again, I have 10,000 of those objects in memory, so my code works. I actually allocated 10,000 objects. Then I called .dispose on all of them. And if we then look at our final snapshot right after running one garbage collection cycle, we will see that there's no more sample disposables in memory. And also if we look at the automatic inspections in the profiler here, we will see that the finalizer queue is actually empty. So instead of having to endure 2 garbage collection cycles, by just implementing disposable correctly, I made it easier on the garbage collector to only run once, or have to run once instead of having to run twice on this collection. Right, so helping the garbage collector will really help in having less pauses or less work for the garbage collector in your application. Now let's look at when we are actually allocating code in our application. Typically, when we're using value types like integers, booleans, structs, spans of t, and things like that, we're not allocating those on the heap, so the garbage collector will not run for those. They are allocated on the stack. And there's a session later today that will cover probably a lot of those things there, so that's perfectly fine. But whenever we are using reference types, whenever we new something, whenever we use say an IOC container that creates an object for us, or activator.createInstance or something like that, whenever we're creating a reference type, we are allocating something in the managed heap, and the garbage collector will eventually have to check that object and see if it can be removed from memory. The good thing is, when we look through our code, whenever we see a new, we know we are allocating something probably on the heap. The problem is, there's also hidden allocations in .NET. I don't know who was in Dina's talk this morning. She talked a little bit about boxing. Well, boxing is one case where you're actually having a value type, but you're boxing it, putting it in a box of a reference type, and you're allocating a reference type for that basically just contains a pointer to the original object, but still you're allocating on the heap, and the garbage collector will have to run for that. So a nice example here is we have the integer, we make it into an object. Well, that means we now have something on the stack as well as on the heap that will have to be collected at some point. If you look at lambdas and closures and task dots and tasks and async await and so on, there's lots of hidden allocations happening there. If you use params arrays, you will see hidden allocations there as well, and there's a couple of more cases out there as well. Now, how do you find those hidden allocations? Well, typically, if you run into a problem, you learn from that problem, and you will hopefully never make that mistake again. You can look at the intermediate language to see what is going on and where hidden allocations are happening. You could, of course, use a profiler and see whatever is happening in your application, or you can use one of the plugins, either for ReSharper or just for Visual Studio without ReSharper, that tell you whenever you are making a hidden allocation. Those two plugins are really nice to look into those things. But just for fun, let's look at some intermediate language code and see what happens under the covers of .NET when we are writing some code. So let me close that demo as well, and then open this one. So what I have here is a very simple class that has a couple of examples where I'm allocating things. And the nice thing is if you have ReSharper installed, you can, where is my tool window? I can search for the IL viewer. And there should be a tool window called IL viewer. And the IL viewer tool window gives me the IL code for the methods that I select. So let me maybe open this one in a separate window. So whenever I select a statement here, you will see that the statement is also selected in the IL viewer. So it makes it really easy to map my C# code to whatever I'm seeing in the IL code. So what we have here is we are boxing. So whenever we are putting this integer inside this reference type box, we are boxing, and you will see in the source code that there's a box statement, and the box statement really converts a value type into a reference type. So that was an easy hidden allocation to find. If we look at the IL code there, we see this thing is being boxed, and we should hopefully find a better way of writing that code. Now, another one that I really like is this one. I think we all write code where we have a method that has that takes a params array of some objects and then does something with that, right? I think we all write code like this. Now, what happens when you call that method without actually passing in any variables into that method? Well, it turns out that if you look at the IL code, that we are actually creating a new array of type string, an empty one, and then pass that into our methods that we just wrote and that expects a params array. So while we may think that we're not passing any variables and not creating any allocations in memory, we are actually allocating a new array of type string that will be passed and has to be reclaimed by the garbage collector. Again, it may not matter, but if you have lots of these allocations, the garbage collector will probably be invoked and will run a garbage collection which may eventually pause your application while it's running. Let's look at another example. Let me move that one aside a little bit more. Imagine I have a method average within bounds that takes an input array, a minimum and a maximum, and then runs a link statement on that basically takes all the numbers from my input array between the minimum and the maximum, and then calls .average on that one. That's perfectly fine code. It's nice and readable, so it looks perfectly fine. Now the thing with this one is that if we look at the IL code, we can actually see that right before I create my link statement, we are actually creating a new object in intermediate language codes of the type display class tree, and we are storing two integers in that object, namely the minimum and the maximum. The thing is, we are capturing the values of the minimum and the maximum because in between here, some things could happen to my code and I want to store the actual minimum and the maximum that I received when this method was first called and when this query was set up. And only when the average runs, I will actually use those variables. So the reason for that, the reasons for this hidden class and the capturing of the values is that anything can happen in between here, but I still want to have the original minimum and maximum when I call the average method in there. So that's a hidden allocation, and again, if you have a lot of those, you could incur some garbage collection when it's not actually needed. So probably this could be a really nice one to rewrite with a simple for loop and pick the right variables and then do the average of that one and not use link in this case. There's a couple more. If you do tasks, for example, if you say a task.run, there will be a lambda created here. Well, that lambda will also at some point create a new object of type display class 4 in this case. Again, a compiler generated class and object instantiation that I have here that will store some of the variables that I will need when I'm running this lambda later on. So all hidden allocations, and some of those we don't actually need in our code and could probably be rewritten to make the work on the garbage collector a little bit easier. And why is my toolbox initializing? Yeah, okay. So back to slides. I'll have to find them here. Yeah. So we've seen hidden allocations, but I want to make a little side note here I may talk to you about not doing those hidden allocations or optimizing your params arrays or rewriting link to for statements and so on. It may not even matter in your code. If something like that happens and is only called once, the garbage collector will run happily and will be perfectly fine in cleaning up the memory that you have. So don't do premature optimization. Don't go home and rewrite all your link statements into regular loops. Always measure, always profile, and see whatever is happening in your code. There's a couple of things that you will need to know before you start optimizing, and that is how frequently are you allocating? If it's millions of times per second, then maybe you want to look into optimizing that. How frequently is the garbage collector running? If it runs every second or every half a second, you probably want to optimize that as well. What generation do our objects end on? That's also an important one. If garbage collection is always on Gen 0, it will be perfectly fine because Gen 0 is typically for objects that have not a lot of references. So garbage collector will be pretty fast on that one. And also, are the allocations and the collections introducing pauses? Is the fact that we allocate a lot of memory causing pauses by the garbage collector or not? That's also something you want to know. You could use profilers for that, but those 4 metrics, you can also get them from performance counters in Windows. So if you just want to look at how your application is behaving, first look at those, and if those reveal something that worries you, then start profiling maybe. But don't go prematurely optimizing all the code that you have. Right, I have another demo here where I say always be measuring, always look into the different things that you have, profile your code, and look at improving things. I don't know if you know this application, it's called Untapped. Who is on Untapped? Any beer lovers here? Okay, a couple of people. I found here in Kyiv that there's not a lot of people using Untapped, so the data set is not ideal. But the idea of this app is that whenever I drink a beer, I check it in, I rate the beer, I tell people where I drank this beer so that other people using this app can find nice beers wherever they are. There's a nice feature for that in the application. Also, for me, it's really nice because when you go to a bar and you check in something, I will see what beer he drank, what he thought about it, so I may actually start trying some other beers. Now, this one on the right is a Belgian beer that I really like a lot. It's my only 5 out of 5 stars on Untapped. And what I wanted to do was create a similar application that requires a lot of data and that stores ratings of different beers and breweries. So I have a big JSON file. Visual Studio crashes when I open it. Notepad++ takes 5 minutes to open the file, and there's basically no way to really look at that thing other than just tailing and taking chunks of this file. The file contains, I think, all of the Belgian beers that exist, a couple of American ones, and so on. And the structure is like this. It's a big JSON array that contains objects that have the name of the beer, that have the name of the brewery, that have the number of votes and the average rating for that number of votes, so that I have some information that I could display in my application. So let's see how we could load that into memory. If we look at our unoptimized version, yes. So we will see that I created an insane version of loading all these beers into memory. Basically, what I want to have in my application is a dictionary of beers where for every brewery, I store the beers and their rating so that I can reuse this at a later point in time in my application. So what I do here is really insane, don't do this. I load the entire beers.json into memory as a string, then parse it into a JSON array, and then start populating my dictionary. I hope all of you see that this is probably an insane way of loading this big file into memory, because in fact I'm loading this big file 3 times in memory and some additional things as well. I'm loading the entire string, I'm creating a big JSON array with all the objects representing all the things that are in this string, and then I'm filling my dictionary and storing them again. So this is probably not a good way of doing things, and I hope you understand that without having to profile here. Now, I created a second version that is more optimized. So in this case, same dictionary, breweries, all their beers and all their ratings. But what I do in this case is I use a JSON text reader that basically streams the JSON into my application. And whenever I encounter an object, I know the structure of my beers.json. Whenever I see an object, I load just that object into memory, then look at the brewery name, the beer name, and the rating, and then start adding it into my dictionary. So that's nice code of loading things, and now I'm not loading the entire file as a string, I'm just loading parts of this file into memory, and that should be more optimized. The important thing to see here is that whenever I load the beers, I'm creating a new dictionary. Why? Well, I just want the new beers, and if the ratings have been updated, I want to have those in the dictionary. So if we profile that application, you will see that the chart of memory usage is kind of interesting. So first of all, you see the beers being loaded. You see lots and lots of allocations happening. A lot of those allocations go to generation 2. Well, that's perfectly fine because I'm storing this in a dictionary that is static and that will live forever in my application. So it's kind of expected that things will end up on generation 2. The interesting thing though is I took a snapshot here when I first loaded all these objects into memory. Then I waited a little bit and I reloaded the objects in memory, which meant that I had my original dictionary, but also in the meanwhile, a new dictionary was filling up, and only when that one was filled up, I discarded the old one and I could reuse the new one in my application. As you can see, that's not ideal because we're basically spending lots and lots of memory there, and there's also lots of memory traffic going on, and imagine parsing a few 10,000s of beers that come from this JSON file. That's a big allocation, and it's almost guaranteed, well, it's actually visible as well, that the garbage collector will run and have to clean up those things and maybe even pause my application. So let's see if we can optimize this thing. So we profiled, we looked at the chart there, and we saw that there's a lot of memory traffic going on, and in fact, I cannot scroll in there, but just believe me, there's lots of memory traffic, and that's inducing garbage collection. Now, we could rewrite our code a little bit, and instead of allocating a new beers array every time we start loading this JSON file, we could also just reuse the existing one. So I have an optimized version, which is almost the same. The only thing I'm doing is checking if the object is already stored in memory. If it is, I just replace the rating and maybe the number of votes. Reason for that is I don't think there's going to be a new beer every 5 minutes whenever I would load this code. And I also don't think that it really matters that the number of votes and the rating is real time. So every 5 minutes, for example, I could load this into memory and just reuse what I already had and just update a couple of values. In doing so, we can see in the profiler, let's go back, the optimized one. We can see in the profiler that the memory usage here is much more flat. Okay, there's the initial load that happens, but whenever I trigger a reload at some point, which happens here, I think, the memory is pretty much flat. It only scans all the objects that are in memory and does some updates, and that's it. It doesn't spend too many allocations, and it doesn't even induce much garbage collection there because of the fact that I'm just updating and reusing the existing objects in memory. The point that I want to make here is that it may make sense in your application to reuse objects and eventually reuse dictionaries and collections and so on, because that may mean that you're doing fewer allocations. In my case here, the shape of my dictionary would probably be the same. The only thing that I would want to have is updated ratings and updated number of votes. So all the rest could be the same. I could reuse the collection and even the objects that are in my collection there. It's called the object pool pattern, if you don't know this one. There's a nice article on that. I think David Fowler also wrote a nice blog post on how they use object pooling in ASP.NET Core, if you want to read up on that. And if you just want a pool of objects that you can reuse, the system.buffers.array pool is a really nice one where you can recycle arrays instead of reallocating arrays whenever you need them. Right. So in summary, the garbage collector is optimized for high memory traffic and lots of short-lived objects. So use that knowledge, don't fear allocations. It may be perfectly fine to allocate lots and lots of objects in your code. When the garbage collector can collect them easily and early, it doesn't even matter. So don't just go and optimize, always measure your application and how it is behaving, and know when allocations happen, and based on that knowledge, look into whether you should optimize this thing or not. Now, let's take a different angle and let's explore the heap. Let's see what .NET is actually storing in memory to see how your application or your memory space works. So how would you build something like .NET, a managed type system that is stored in memory of a computer? and that is both CPU and memory friendly. How would you build something like that? Well, probably you would go with something that resembles a relational database. You would probably have a table that stores information about the type. I have a class named person. This person has 3 properties, name, first name, last name, and maybe age. First name is a string, last name is a string, age is an integer. Information about the types that you have in memory. Then you would probably have another table that just contains the values. So for my person, there would be the value Maarten Balliauw, my age, and I could run a query that basically links the values and the type information together whenever I'm running my application. So you get some sort of a relational database to build something like that. Probably you'll have another table that stores method pointers, like where can I get, for example, the create new person or the constructor of this type object and so on, and some other inheritance things, for example, like how is the type structured, is person a subclass of something in the application, things like that. Well, it turns out .NET works very, very similar to that structure. So if you push stuff on the stack, not managed by the garbage collector, whenever you allocate something, what you will get back is an instance ID. .NET will work with that instance ID and follow that instance ID to a pointer with the values that live on the stack. So that's something that happens in there. For everything on the heap, you will see some table structure. You also get an instance ID that points to a table that contains just the values of your type, as well as a pointer to another table that contains the type information and the methods and so on that are in the type that you are making use of. So that's nice. .NET really works like a relational database internally. It has different tables that are linked together. Now, theory is nice. Let's see if we can actually explore this method table or explore this table in memory and see whatever is happening in there. There's a nice NuGet package called Microsoft.diagnostics.runtime that you can use for this, or ClrMD, which was the code name, I think, for that one. And it allows you to attach to a running process, pause the world, pause the entire application, and see what is in memory. My short definition of that one is linked to Heap, because you can actually query what is in memory at some point in time. So let's look into ClrMD. I need my other Visual Studio there. So I have a solution here that has 2 projects. One is the one that I will be using to explore what is in memory, and the other one is a target application that I will run to do some things. So my target application is quite simple. All it does is write something to console, create a timer, creates a type that I created called clock, and whenever the clock ticks, this method is executed and I write the current date time to console. And basically, almost immediately after allocating my clock, I run garbage collection and I expect my clock to be gone from memory, etc. So if you run this, this is the most boring demo application ever. But if you run this, you will see, it shows up on this screen. You will see that it prints something, it runs a collection, and even after the collection, it's still running my timer. So you already see something is wrong with this application. But just to give you an idea, I have an application that prints the time. Awesome. Then in my other projects, what I'm doing is I'm basically starting my demo application. And what that does is it simply opens the application and gives me back the process. So I have a process ID that I can work with. And when I run it, I start the other application, I wait for a couple of seconds, and after that wait, I attach ClrMD to the running process. So attaching to the running process works based on the process ID, so I needed the process ID there. And I'll wait 10 seconds for it to attach in case it takes a while to attach. Now, one important flag that I'm passing into ClrMD is the fact that I'm attaching in an invasive manner. Whenever I want to explore the memory space, it would be very, very unhandy and very difficult for me to analyze what is going on in the application. If the application would still be running, the garbage collector would be running, memory could change, and so on. So by passing this invasive flag, I'm actually telling the runtime, pause the world, pause everything, and give me a static representation of what is in the application so that I can reason about that one. So let's maybe just run it and see what comes out. So my ClrMD process will start, my actual application will start as well. And as you can see, after about 2 seconds, I attach to it and you see the application really being paused and the date time is no longer printed to console there because I use this invasive flag. Now, in source code, what I can do is I can use this data target that I get from ClrMD to inspect lots and lots of things that are in the runtime. So the first thing that I could look at is, for example, the CLR info. Which version of the CLR am I using to run this specific application? It gives me back the version, in this case .NET 4.7, as well as the DAC file. That's a data access file. Look at it like the data layer from runtime towards the actual stuff that is in memory. So every single version of .NET has this DAC file that you have to use. Anyone has used WinDBG and SOS before? A couple of people. This file you would normally have to load as well. What ClrMD does for you is download the correct file to work with, so it's actually easier than working with WinDBG. Now, other things that I can do is dump runtime info. So what I can do is explore my data targets and dump, for example, the number of threads that I have, and for every thread, check if it's a background thread or a foreground thread, and then print the entire stack trace of that thread. So let's do that and run it. We get all the threads that are running in my demo application. There's a background thread that does a console.read line at some point. And I have some other background threads. I don't know what they are doing, but they're there. Other stuff that I can do here is, for example, dump the objects that are on the heap. Now that's a really impressive one, actually. I can get all the objects that are in memory of my running application. I get back the different generations. I can look at what's in Gen 0, Gen 1, Gen 2, and so on, and get information about the objects. So the way this works is that for my heap, I can enumerate all the object addresses, this initial pointer that I had in that table. Then for every pointer, I can get the object type, make the link to this other table that has the type information. And whenever I actually have a type, I can call type.getValue for this specific object address, and then I will navigate yet another table to get the actual values of the objects that I have in here. The nice thing is, for simple objects like strings, I can just print strings to console, so you will see, for every string, you will see the value in there as well. And for more complicated objects, I would have to do some things to read the actual values in the object, but it's doable using this approach where you navigate from pointer of the object to the type to the values that are in the type. Right, let's look at another one. I could also dump string duplicates. So I could look into memory and look at duplicate strings in my memory space. So if we run this one, you will see that there are a lot of string duplicates in a default application. So you will see there's 16 usages of the month of May in Dutch. I don't know why there's 16 instances of that one in memory, but they are in memory for my very simple Hello World application. And so on. The way this one works is pretty similar to the previous one. Again, I enumerate all the addresses that I have. Then I get the object type. If it's a string, I just count the number of strings. I get the value of my string and then add them into a dictionary of unique strings and set the number +1 so that I can count the occurrences of this one. There's another one that I can do, and that is dumping retention of objects in my memory space. So let's quickly jump back to the profiler. And let's maybe first look at the source code again. So in here, I actually created a memory leak. I think a lot of you will spot the memory leak that I created here. Even though I'm expecting this class to be disposed at some point and be collected by the garbage collector whenever it runs, there is still a timer that references my onTick, and I should actually close my timer or dispose my timer as well if I want the object to disappear from memory. This is very, very visible if you look at it in a profiler. If we would take a snapshot of my object, you will see that my clock is still in memory because there's a timer callback linking my clock, and it's in memory because of that. Well, the thing is, with ClrMD, I can write similar codes that dumps the retention path to my clock, and you will see that my clock is being held in memory by a timer callback, a timer queue helper, and a timer queue. And I could even chart this and show a nice chart of what the retention path to my clock looks like if you use any charting library. So that's kind of nice to work with. The way this one works is slightly more complicated, but the idea is that in my program here, again, I enumerate the heap. I first try to find my clock. So whenever I find my clock, where is the code there? Should be in there. Anyway, let's search for clock. So whenever I have an object that matches my clock type name, I will start enumerating the entire heap and basically build the tree of objects that are pointing to my object, to that object, and so on, to basically get that information that the profiler gives me as well. Now, you may be wondering, what's the use of that? It's all nice, it's nice and geeky, and I can look into the memory space, but why would I do that? Well, turns out that having that programmatic insight into your memory space can be quite useful. You can attach to any running process, or you could use ClrMD to attach to a dump file, for example, and you could check whether an object is still in memory where you expected it to be reclaimed by the garbage collector. So for example, if you have a memory leak at some point, you could analyze the memory leak, then write a unit test that uses ClrMD or something else to check whether the fix that you are creating will actually solve that memory leak, and then programmatically check it every time you have a test run going on, so that you can be sure that you're not really reintroducing a new memory leak later on. ClrMD is one way to do that. There's another way, that is .memory unit. That's one that we use inside JetBrains. I have a nice blog post there where the idea is that you can write a unit test, and let's try to zoom in a little bit, where you can write a unit test that basically captures a memory snapshots, and just like in the profiler, gets the objects from my snapshots, checks if the type is a clock, counts the objects, and then checks if the clock was actually removed from memory at the point that I wanted to remove this one. So that's another way of doing this, but if you're really into ClrMD, you can write something like this yourself as well. So in conclusion, the garbage collector is optimized for high memory traffic and short-lived objects, so use that knowledge, use the garbage collector, don't fear allocations because I told you to fear them. It's perfectly fine very often. But if you suspect something is wrong, or you see Gen 2 pauses or things like that, then you could start analyzing, measuring using a profiler, using things like ClrMD and so on, and look into how you could optimize your code, but don't prematurely optimize. With that, I have a tip for a next talk. There's another one by Nikolai later today that will explore more of the stack side of things. So go there if you're interested in this topic. And if not, thank you for being here and enjoy lunch later on. Thanks. Yeah. So, any questions?
Thank you, and I have two questions probably. First question, why 3 generations? Why not 4, 5, and so on? There are a lot of information, but basically it's not really clear how it was calculated. And second one, so as I understood, you can basically attach to any process and serve memory and data. So what if I don't want, if I'm writing a computer game, right? I don't want anyone to attach and read some data and so on. How I can protect my application? Yeah. Thank you.
So on your first question on why are there 3 generations, I think it's just an arbitrary number that Microsoft in this case chose. It could be 5, it could be 10, but if it would be 10, for example, someone in the audience would ask me, why are there 10 generations? So they just decided on a number, I guess. And I think it also sort of makes sense where you have short-lived objects, medium term, where after 2 collections the object could be reclaimed, and then everything else. It gives a nice balance, I think, between CPU usage and the number of times that the garbage collector has to actually pause your application to run garbage collection. On the second question, how do you prevent people from attaching to your memory space? Not. So whenever you run your application, it's running in your machine, and .NET gives you the entry points into that information, so it's always possible for people to do something like this. The only way to prevent that from happening is running your process elsewhere. So if you have a server application, if it runs there, the client cannot reach out to the memory space of the server there. But it's always possible to attach. Yeah.